Okay, guys, first thing you're going to do is you are going to color code all of these different little boxes. I know you might not know yet where the alkali metals and the alkaline earth metals and some of this stuff is, but just put your little color coding in the box. Notice that the ones that we say transition and other metals, we're just going to leave white. Okay, so alkali metals, we're going to do blue, alkaline earth, purple. These two guys, we're going to leave white. Metalloids are going to be green. Halogens are going to be orange. Noble gases are going to be red. And any other just non-metals are going to be yellow. Okay, the first thing that you're going to do really after you do this little key is you're going to take a marker and you are going to outline the metal section with a blue marker, outline the metalloids with a green marker, outline the non-metals with a red marker. And I'll show you what that looks like. Hang on. Okay, so once you do your marker outlining, this is what you should have. Notice I haven't shaded anything yet, but we'll get to that. I also went back over the little stair step with a black marker to make it nice and obvious because it kind of gets lost. Okay, but what you're doing is you're doing your metals in blue, your metalloids in green, your non-metals are in red. And notice that hydrogen, even though it's over here, is a non-metal. So make sure that you put a little red box around hydrogen because it's a non-metal. Okay, in addition to noticing that hydrogen should have a red box around it, I want you to also notice aluminum, which is right here. Aluminum is right under this little stair step, and most of the things along the stair step are metalloids and they're going to be green. But aluminum is a metal. So make sure that aluminum has a blue box around it. So the blue is going to go up and around the aluminum and all the way down to this corner here. Okay? Okay, and while you guys are looking at the main outline with the three marker colors, I'm going to go ahead and color in my metalloids with my matte pencil because that's real easy because all of those are going to be colored in with a light green matte pencil or just a green matte pencil. Okay, so I went ahead and I shaded with my matte pencil. Please do not color these in with markers. It'll be too dark. You can't see everything. So I shaded everything that is a metalloid. I shaded those green, and I just had a question about whether I should be using an orange or a yellow marker for anything, and the answer is no. We'll move to matte pencils and we'll have some of that, but for the markers there's only three colors. There's blue for the metals, green for the metalloids, and red for the non-metals. Okay, I'm going to flip to the back so that we can do the key, and then we'll come back to the front and color code everything properly. Okay, so even though I didn't use Sharpies, I did have a little bit of bleed through, so we're just going to have to deal with that. If I'd used Sharpies or something, it'd be even worse. Alkali metals are blue. Alkaline earth metals are purple. Leave these two white. This one's already been shaded green. Halogens orange. Noble gases red, other non-metals yellow. I haven't told you where these are. Just fill in the key and then I will show you where they are. Okay, so I've got the key filled in. I actually picked light blue so that it was more obvious the difference between my blue and my purple because sometimes they look similar. But anyway, I've color coded it. I've left these two white because those are all of my well, that's most of the metals. And then when I flip it over, here's what it looks like. Again, all of my non-metals are in the red marker border, but some of them are just, your garden variety non-metals. And then this column 7A with fluorine, chlorine, bromine, and iodine, those are my halogens. Halogens are actually very reactive nonmetals. Column 8A are my noble gases. My noble gases are actually nonmetals that don't react with anything, and the reason why they don't react with anything is they have all of the valence electrons they already need, so they're not going to be reacting to look for any or to get rid of any. which is really what chemical reactions is all about, as we'll find out. Over here, this blue column, column 1, is my alkali metals. Notice that even though hydrogen sits in this same column, it is not a metal. So you might be asking yourself, why on earth is hydrogen over here in the first place if it's a nonmetal? Well, it's placed in this column because it has one valence electron like the rest of the guys in this column. Everybody in column 1 has one valence electron, and they're all, including hydrogen, very reactive. Column 2 are your alkaline earth metals. They are also reactive, not as violently reactive as column 1. But those are your alkaline earth metals, colored in purple, and they'll have 2 valence electrons. Okay? We don't worry about trying to figure out the number of valence electrons for the short columns because the rules for those are a little bit different, and we won't mess with that. Y'all aren't in chemistry yet. You'll probably learn some of those details in high school. So most of the table we actually outlined in blue, but we left it white because those are most of our metals. And we're only distinguishing these 2 columns of metals, the alkali metals in blue and the alkaline earth metals in purple. So you guys know me, I tend to color code everything. So here's kind of what I did. I did my little blue border back here, and I pointed out that that's metals. My green border, that's metalloids. My red border, that is nonmetals. And then here's what I did on the front. I made a key. The red border is nonmetals. The green border is metalloids. The blue border is metals. Then I also went and labeled the tops of these tall columns. Why do I have numbers there? Well, everything in column 1, all of those elements have one valence electron. So the VE stands for valence electron. So everything in column 1 has one valence electron. Everything in column 2 has 2 valence electrons. I put a bracket around what's known as the transition metals, these short columns. And remember, we don't worry about trying to figure out how many valence electrons for them because the rules are a little bit different, and that we'll save for high school chemistry. Everything in column 3 or column 13 has 3 valence electrons. Everything in column 4 has 4 valence electrons. Everything in column 5, 5 valence electrons. Everything in column 6, 6 valence electrons. Everything in column 7 has 7 valence electrons. And everything in column 8 or column 18 has 8 valence electrons except for helium. So you might be asking, well, why did they put helium in column 8A when it doesn't have 8 valence electrons? If you think about helium being element number 2, as long as it's neutral, it's going to have 2 protons and 2 electrons. And it just so happens that the maximum amount of electrons that you can fit in that first energy level is 2. So the only energy level that helium uses is the first energy level, and it's full of electrons. And when you're full of electrons and you don't have any room for any more, that's when you're unreactive. So helium is unreactive, just like the rest of these guys. They're all unreactive, neon, argon, krypton, xenon, and radon, because they all have 8 valence electrons, and that's full for them, okay? Helium is full at 2 because helium is only utilizing that first energy level, okay? So I want you to add those. And then at the very end, we're going to flip it over, and we're going to talk about what else to fill out on the back with the key. Okay, we have talked about this before, but I'm going to remind you guys that this is the case. The element's period number, the row that the element is in, tells me the number of energy levels I have to use to place all the electrons. For instance, hydrogen and helium are in row 1 or period 1. They only need 1 energy level to accommodate all of their valence electrons, because they only have 1 or 2 valence electrons to begin with, or total electrons. Okay? The element's group or column number tells me the number of valence electrons. So the period number tells me the number of rings or energy levels. The element's group number tells me the number of valence electrons. Okay? And we've just done this on the front. Okay? Group 1, your alkali metals, everybody in that column has 1 valence electron. Everybody in group 2 has 2 valence electrons. Everybody in group 13, or otherwise known as group 3A, it's going to have 3 valence electrons, 4, 5, 6, 7, 8. The only exception is helium, which sits in group 8A, even though helium only has 2 valence electrons. Okay? Okay, so one more time, just in case I didn't go over with the mic on. The period number is going to tell me the number of energy levels or rings that we have to use to place all of our electrons. The element's group number is going to tell me the number of valence electrons. So for instance, everybody in group or column 1 has 1 valence electron. Everybody in group or column 2 has 2 valence electrons, etc. Do we worry about the short columns, the transition metals? No, because the rules for them are a little bit different, and you'll learn more about that in high school chemistry. Okay, then the last thing I want to say, again, for those of you who are in here with me, this is the second time I've said it, but for those who I'm recording this for. This note is really important. Helium is in group 18 or group 8A. It has only 2 valence electrons, but it is still a noble gas because its outer energy level is full and is therefore unreactive, just like other noble gases. Okay, so you guys have already said it once, but say it again. When is something unreactive? When the outer energy level is full. It will be reactive when its outer energy level is not full, and the atom is going to need to gain or lose electrons to become more stable. Okay, it may lose electrons and drop down to a full energy level. It may gain electrons in order to fill the outer energy level it already has, that kind of thing. Okay? All right, so bottom line is the backside of your color-coded periodic table should look like this. The front of your periodic table should look like this. And if you've got all that and all the notes, then you should be good to go.